Enthalpy, activation energy, complete combustion, incomplete combustion, initial temperature, flash point. Student, we're going to look through this term. What is activation energy? Activation energy is the energy that you require to bring a reaction to happen. The energy that you require to bring a reaction to happen. What's that mean? Let's explain. In some molecules, they have lower activation energy. Those types, they usually react pretty quickly at room temperature. Example, sodium react with water. They will react pretty quickly, violently. So if you put sodium into water, do you need to put it under the stove to heat up the sodium or heat up the water to make it react? No, you don't need to. Long as you put sodium with water, you don't need to add any energy. You don't need to add much energy, and they will react. The point is, you are not required to add much energy, and the reaction will happen. And now let's look onto the graph. If you look onto the graph, you see, first we learned heat of reaction in the past. This substance, it will release energy. It will release from here to here. So this substance, sodium react with water, you expect energy will produce. You release heat. But now we learn on this activation energy harm. What does that mean? That means you have to add a little bit of energy to make the reaction happen. You need to add a little bit of energy to make the reaction happen. So do you need to add much energy? Well, at room temperature, the room is already enough energy to bring this reaction happen. So the point of activation energy is to talking about, at this stage, how much energy do I need to add in so that this reaction will, when it's over the hump, the reaction will just happen. The reaction will happen. Then now let's contrast with another example. You will find in another opposite case, some molecules, they have very high activation energy. And you will say like the methane with oxygen. They have very high activation energy, but they react pretty slowly. And actually you don't see it happening without adding energy. Like methane with oxygen, or even some petrol mixed with oxygen. Okay, when they have that mix, will they, as you know, we learned that all the fuel with oxygen, it produces a lot of heat. Yes, it does produce a lot of heat, but the point is, if they react, they will produce a lot of heat. As in this graph, if they react, it will produce that much of heat. That is the delta H. If it reacts, it will produce that much of heat. But the point is, do they react? The point is, they do not react at room temperature. So if you put the methane gas, turn up the Bunsen burner, let the methane gas come out, mix in the room, will they suddenly burn up? No, the room becomes full with methane gas. And does it burn? No, it won't burn. The room it becomes very smelly, but it don't burn. So, how do you want to make it burn? If you, this methane with oxygen, if you add heat, if you add energy. If you add energy, how much? If you add that much energy, once the energy reached up to this stage, yes, it will react. When it reach up to that stage, you add that much energy in, it will react. So student, do not confuse with the word activation energy with heat of reaction, delta H. Delta H, heat of reaction, is to talking about when the substance reacts, how much heat it will produce. When the substance reacts, how much heat it will produce. Like in this substance react, how much heat it will produce. Activation energy, on the other hand, is not talking about how much heat it produces. It will say, you want this chemical reaction happen, how much heat you need to add to make this chemical reaction happen. And in this case, you need to add a little bit energy to make this chemical reaction to over the hump, and chemical reaction can happen. In this case, yes, you know, oh yes, it will, if it burns, it produces a lot of heat. But is it easy to happen? No, you have to add a lot of energy in the beginning to bring this reaction happen. So define what's meant by activation energy. Energy you need to add in to make the reaction, to bring this reaction. On the top graph, what is the energy of product? 100. As you can see, this is the energy content of the product. What is the energy of the reactant? 510. Where about is it? This is 510. So you have that much energy and you will release that much energy. So now we're talking about what is the enthalpy change. Enthalpy change is 100 minus 510 give you 410 kilojoules. Look, we're counting just only from this level to this level. And what is the activation energy now? 90, which is activation energy is counting how much energy you need to add to make this reaction happen. So you have to add in that much energy. Once you have that much energy, the reaction will happen. That's activation energy. Let's do another example. On the bottom graph, energy of the product, how much? 100. As you see, 100. What is the energy of the reactant? 200 here. So what is the enthalpy change? Minus 100. So that is the enthalpy. And how about what is the activation energy it requires? 500. As from 700 minus, as with 700, here 700, you need to have add that much energy as from 200, you have to have that much energy. So you need to add 500 energy to bring the reaction happening. So on these two calculations, you can see enthalpy change is different from activation energy. They are two different methods. Enthalpy change is just only look onto how much content of energy when they released. Activation energy is talking about how much energy you need to input to add to bring a reaction happen. Now let's do one more example. On these two similar graphs, question 1, which one requires more energy to initiate? In other words, which ones need more energy to make the reaction happen? B. Because on the A, you need to put only a little bit energy. B, you have to add a lot of energy to make the reaction happen. Question 2, which one release more energy to the environment? Which ones will release energy more? A. So how much energy you calculate originally from this energy will release to this energy. So this one will release more. And how about the bottom one? You only calculate from here to here. So this is released a lot less. So student, I hope now you get clear about the term heat of reaction, or called enthalpy change, and which different from activation energy. Now let's look on to another word. Combustion. Combustion of this is talking about anything you burn with oxygen and you will produce heat energy. Combustion formula also exothermic. As on the table, you can see of this list of matter, they all react with oxygen. S2 K react with oxygen, Fe react with oxygen, magnesium with oxygen. Combustion means the substance who react with oxygen. And they will have a formula. They all will form into the substance oxide. And the energy always released, and they are exothermic. And at the bottom of the list, any hydrocarbon fuel, when it combines with oxygen, it always will give one formula: carbon dioxide and water. And this is called the combustion formula. And have we done any combustion equation? Yes. As example, you have a magnesium, a strip of magnesium burn in air. It will give you a very bright white light. Or you can have a butane burn in oxygen. That's happened to your lighter. It also gives carbon dioxide and water, and they all release energy. Exothermic. Complete combustion. Incomplete combustion. What does that mean? Any hydrocarbon combined with oxygen, they all give carbon dioxide and water. So the formula is any hydrocarbon with oxygen give carbon dioxide and water. And as you see on the Bunsen burner, when methane with oxygen, you will give a blue color flame. Okay. What is incomplete combustion? Incomplete combustion is when this fuel, hydrocarbon with oxygen, but is insufficient oxygen, not enough oxygen. In that case, it's going to produce carbon monoxide and water. Insufficient oxygen burning, it gives carbon monoxide and water. Student, you don't need to pay too much attention about the ratio because all equations will be different. But the whole theme of the equation is any hydrocarbon in complete combustion, hydrocarbon with oxygen all give carbon dioxide and water. Incomplete combustion is not enough oxygen, they all give carbon monoxide and water. Why we talk carbon monoxide? Because carbon monoxide is scary. Carbon monoxide is a pollution. It is colorless, odorless, toxic gas. So in case if you breathe in too much carbon monoxide, you can faint, pass away, and you will die. So carbon monoxide is a very toxic gas. Student, I'm going to teach you the word initial temperature, flash point. What is the meaning of these two words? Let's start. Initial temperature. Initial temperature means the temperature you need to bring this fuel air mixture to burn spontaneously. To burn spontaneously. What's mean by burn spontaneously? That means these things will suddenly, by itself burning. By itself burning. What do I mean by that? I give you an example. Imagine you have a pan, you fill it with petrol. You put it under a hot summer sun for the whole afternoon. Do you think it will burn? No. The answer is no, it won't burn. It's not hot enough. Okay, if it's don't burn, let's try more. This time I put this petrol of the pan, I put it under the stove with fire. And now I'm heating up the pan. The pan is getting very, very hot now. Now the question I ask, do you think this petrol will burst into flame? We call burn spontaneously. You will suddenly burst into flame and burning? I tell you the answer. No, it's still not enough temperature. Okay, let's try harder. I turn it into the maximum heat on the stove. It's getting very, very hot. The petrol almost start to be bubbly. Very, very, very hot. Now, do you think it will burn? Will suddenly, this hot petrol will suddenly burst into flame? The answer is no. It's still not enough temperature. Then you will be so surprised. Well, I thought petrol is something very dangerous. You will burn and very scary. Yes and no. Look, if you leave it at a room temperature, it will not burst into flame. However, if you increase to 390 degrees, yes, this petrol will burn spontaneously. It will burst into flame. Then, what is 390? What is 390 degree? I tell you what, 390 degree, your home cooking stove, your maximum temperature is only 190 to 200. So you're still short by 100. So what does that mean? Petrol are not easily burned. So don't think petrol as that danger that you will burn so easily. No, petrol are not burning easily. So even you see some petrol very, very hot, 100-degree hot petrol, they don't burn. They won't burst into flame. No. So here I have a graph to show you on the top 1 to 8. They are all the common this is the common field. You see what is the ignition temperature? You will find that they all will go above 200. What does that mean? That means, look, your cooking stove maximum temperature is about 200, and you need about double, 390. For this petrol will hot enough become burst into flame, and that means petrol are not as dangerous as you think. And so what did you learn from here? Do you remember activation energy? That means petrol, methane, all these gas, yes, they all release energy when they're on fire, but they have to add in a lot of energy. So would they be burst into, you want this happening, you have to add energy. If you add 390 degree to up to that temperature, yes, it will happen. But you need 390 as in petrol. So that means, how are we going to make the petrol burn? How are we going to make the petrol burn if the petrol so stable it doesn't burn? Okay, now we look onto another word. That is flash point. And what is a flash point? Now let's see. We see flash point. What is flash point? Flash point is how much temperature required if this fuel and air mixture to burn, if it contact a spark. If this petrol touch a spark, tiny weeny bit of spark, you don't need to touch a big fire. You touch a tiny weeny little bit of a spark or a flame. And what will happen? It will burn. It will burn. The point is, even you say petrol, you heat it up, it's not easy burning. But if the petrol touch a spark, a tiny bit of a spark, it will be on fire. So flash point is very scary. That means petrol, if the petrol being hot, is not scary. But when petrol touching a spark are extreme scary. So here is the temperature of flash point to show you, look, even you are in a one very, very cold temperature. You see all the flash point temperature are all -degree. That means even in a very cold day, you are in a cold winter night, 0 degree, you say, oh, the petrol is icy cold. Okay, if this petrol touch spark, it still burn. Even in a cold winter night, that you touch the petrol, it is cold like icy cold water. But if this petrol touch a spark, it still can burn. So, and sometimes you see how come there is a lot of accident happen. The kitchen, the petrol, the oil, cooking oil catch fire in the kitchen. What happened? Does the petrol really heat up to 290 degrees? No. What it happened is when the petrol boiling, and it spill and touching the fire. When the cooking oil spill and touching the fire, then it become the flash point. Now, once you have the flash point, it will just burn. So the kitchen will be on fire. So you can see a lot of all the natural gas, petrol, they all have very low flash point. That means they can be very, very easy to catch fire, even in very, very cold environment. So ignition temperature are pretty safe. Petrol are not easy just by getting hotter and hotter and will self-burning and become inflamed. No, the petrol being hot would not cause it to catch fire. But the bottom one, flash point, when the petrol touch a spark or a tiny flame, it will cause fire and even explosion. So you see that in the petrol station, they always have a sign warning the driver to extinguish cigarette, no smoking, because if any spark accidentally touch onto the petrol, it can cause serious explosion. Even you say this is so the petrol is cold like icy cold, still problem will cause.